Hello everyone. Welcome to welcome to the 111th nice talk today. Thank you all very much to join this talk at Monday evening at New York time and Tuesday morning in China time. And today, let's welcome our speaker, Jiarui Liu. He is a first-year PhD from Carnegie Mellon University. His advisor is Professor Mona Diab, and his research direction is reasoning and alignment for large language models and natural language processing for social good. So today he will talk about stabilizing reinforcement learning for honesty alignment in large language model on deductive reasoning. So now let's welcome Jared for his presentation.
Cool. Thank you, Wenyu, for introduction. So right now, let me share my my screen. Could you see the screen? Yeah. I'm Jiarui, and this paper is my summer internship project from and this paper is about honest and the paper is already on arXiv right now. Right. So to give a brief overview of this paper, we introduce a method named anchor. Namely, it anchors reasoning trajectories into GRPO's rollouts for honest deductive reasoning. So as a background, existing methods such as SFT or GRPO, they are not trained to be honest when answering reasoning questions. So in the figure shown here on the left, if a question is unanswerable, the language model should not try to answer it. So if the model is honest, it should abstain from answering the question. And if the model is being dishonest, it will try to hallucinate some answer for this unanswerable question. So in our paper, we introduce an approach that improves honesty in this setting. And we will introduce the method later in more details. So as a brief background of the definition of honesty, so previously back in like 2020 or 2021, there was a Anthropic paper that defines the alignment aspects for language models. So in addition to letting the model be helpful and harmless, they claim that model should also be honest. This means that models should know when they lack sufficient information to generate the answer, and the model should avoid fabricating answers to those questions where it doesn't know the answer. This means that the model should both have the two capabilities listed here. First, the model should be aware of their own knowledge boundaries. So basically, if this question is about something factual, and if the model internals doesn't have this knowledge, the model should not try to answer the question. And another category is that the model should also recognize whether a question itself is answerable or not from the given information in the user prompt. So these two points focus on different sides. The first one focuses on the model's knowledge itself, knowledge boundary, and the second one focuses on the question answerability. So previous work for honesty alignment, most of the benchmarks that claim they do honesty evaluation, they often conflate the two aspects of honesty shown in the previous slide. So basically, it means that those benchmarks, they both try to test whether the model can be aware of their own knowledge boundary, and they test the model's refusal to answer the question if the question is unanswerable. So this case makes it difficult to evaluate the second dimension in isolation. So in our work, we focus exclusively on the second dimension, which means that we isolate the model's pure reasoning capabilities for the question answerability from factual recall. And we achieve this by focusing on deductive reasoning settings. So we will explain later like why deductive reasoning is a good test bed for exclusively studying the second dimension. And our focus of honesty is defined here, where a model should provide an answer only when the conclusion is logically entailed, and the model should abstain when the premises do not support the valid derivation. So following the previous slide, our so we choose deductive reasoning as the reasoning task in our paper because deductive reasoning, by definition, it derives conclusions strictly from the given premises. So this will avoid the model to use any external knowledge that are not provided in the user prompt. Basically, it means that if all the premises are provided in the user prompt, and there is some graph structure that can be constructed from the user input, there will be a conclusion that is guaranteed to be true if the necessary premises are true. So namely, a conclusion is valid only if it can be obtained through a sequence of inference steps based on the premises. And this setting isolates honesty from factual recall. Basically, it means that we define all the premises in the user prompt explicitly so that the model do not need to rely on its own inference on factual knowledge. And another line of related work is about stabilizing RL algorithm. So supervised fine tuning, it has been popular for a long time, and it's still popular for now. And SFT can quickly align models to some target distributions. But for reasoning tasks, there are a lot of papers criticizing that SFT often overfits to the demonstrations given in the training set, and they fail to generalize because of their training objective limitations. So instead, reinforcement learning methods such as GRPO, they optimize for verifiable outcomes, and they show a perfect performance since earlier this year. And one issue of the GRPO algorithm, particularly, is that for GRPO, when all sampled rollouts are incorrect, when we calculate the variance, it will be 0. So when it comes to the gradient update, the gradients will collapse, and there will be no learning signals for the model to optimize for. So to solve this issue, multiple methods, they try to combine SFT and GRPO. So some examples are trying to having designing some loss terms that mixing both that taking into account both SFT and GRPO gradient updates. But those methods, they either lack ground truth trajectories for guidance, or they still fail to stabilize policy updates for the 0 variance issue. So after the literature review of the current algorithms, our motivation is that we need to propose some new methods that can make good use of the ground truth trajectory if it's available for this honest deductive reasoning setting. So we construct 2 multi-step reasoning datasets for honest deductive reasoning task. So the 2 datasets contain both answerable and unanswerable queries. The first dataset is graph LA. It's a linear algebra based dataset where the answer requires solving chains of equations, and as the figure illustrated here, we have some unknown variables B and F, and we have an edge that connects these 2 nodes through a linear equation. So this is how graph LA look like when it comes down to the actual edge relation for the 2 nodes. And here, unanswerable cases are created by randomly masking the sum of the edges in the graph, making it impossible to solve the linear equation when we ask about the final unknown variable. And the second data set we explore is a logical inference data set where the queries depend on composed implication chains with unanswerable instances produced through several strategies that will be explained later. But basically, here the relation between the 2 nodes are connected by some logical inference rules. So those are basically propositional logic that tries to connect the 2 nodes so that if we have a premise named F and we know that F is true, then according to this edge relation, we will know that B is true. So this is how we constructed these 2 data sets. But this is just a brief intro, and we will explain furthermore later. So based on those data sets, we try to answer 2 research questions. The first research question is that how do untrained models perform on reasoning tasks like proposed on the previous slide of varying deductive difficulty? So by saying deductive difficulty, I mean when we construct those data sets, there can be different number of variables. There can be different number of depths from the the first premise to the final conclusion. So all those parameters will lead to different difficulty of the data set when the model tries to answer whether the conclusion is true, or when the model tries to answer the actual value of the conclusion node. So the first research question will serve as our motivation because there's no training here, and we just do prompting and we test existing models how well it perform on the current data set we build. And the second research question is about how can training equip models with honest reasoning capabilities. And this will be our core research question. And we will explore our algorithm named Anchor here. So in summary, we have three main contributions. First, we formalize the honesty in deductive reasoning as the ability to abstain on unanswerable queries and answer correctly on answerable queries. And we introduce two data sets to test this capability. And second, we propose a method named Anchor, which injects ground truth trajectories into GRPO rollouts. So we will explain later about this method, but yeah, as you can see here, like basically Anchor is just injecting ground truth trajectories into GRPO's rollout. And this way, we can unify the supervised and RL learning signal. And lastly, we demonstrate that Anchor stabilizes reinforcement learning, and it performs like better on the two data sets compared to several baselines. And through some analysis, we find it enables honest abstention on the data sets, and we have some interesting analysis later. So to start, we have two data sets, right? So we want to construct these two data sets. So before having any concrete implementation, we have some requirements in mind. So first, the data set must contain both answerable and unanswerable examples, because if we want to study honesty, there must be some examples that are unanswerable so that we can know that in those cases, the model should answer with something like I don't know or unknown, instead of trying to make a guess of the answer, namely hallucination. And the second requirement is that we want to have examples that involve multiple reasoning steps. So multi-step reasoning allows us to stress test the models by varying the parameters, for example, the number of steps involved to test about the model's upper bound reasoning capability. And the reasoning should also be deductive because, as mentioned in our motivation, we want to isolate the pure reasoning capability from factual recall so that we can like more explicitly understand what the model relies on to perform those reasoning tasks. So we formalize the deductive reasoning tasks using directed acyclic hypergraphs. So basically, hypergraph means that there will be like a hyperedge, and it links a set of premises to a single conclusion. So for simplicity, you can just think about it as a directed acyclic graph. And here we allow the only difference is that we allow multiple premises to jointly satisfy an inference and lead to a single conclusion. So the query is answerable if there is a valid path of hyperedges the query, namely conclusion, from the root premises. And in contrast, the query is unanswerable if no such path exists. So in our paper, to construct the ground truth trajectory, since we need those ground truth trajectories for training SFT for comparison, and also like using the ground truth trajectories in our method. So we have to construct the ground truth trajectories for those data set beforehand. So we perform a DFS search on the graph, so that it exhaustively explores the graph and ensures that the true reasoning path is visited, but every other passes are also explored before exploring the true reasoning path. So this means that this ground truth directory will yield a complete reference derivation. So more specifically about the dataset construction details, graph LA for linear algebra, it instantiates the deductive reasoning framework using chains of linear equations expressed in natural language. And basically, this requires model to traverse the correct reasoning path and ignore, or some better words like learn from exploring the error or the wrong edges. So the parameters involved here are total number of variables, the reasoning depth, and coefficient. So the coefficient ABC are the multipliers and the final like the values on the right hand side of the equation. Those are like some integers in our case, and the variable value are also integers for the variable B and F here. And there are several other parameters. Oh, okay. So one thing to note here is that for unanswerable cases, we have another parameter named cut depth. So basically, imagine we have a directly acyclic graph, and there exists a path that connects the premise to the final conclusion through a long multi steps. So here the cut depth means that for unanswerable cases, we will randomly mask one of the edge for the ground truth trajectory, and these steps means how far the like where we cut the edge is from the final conclusion. So basically, if this value is larger, it means it's harder for the model to solve the problem. And for constructing the second data set, it is for like logical inference, and for unanswerable instances, they are created by applying interventions on the edges. But we have some like different strategies here. For example, not only we try to remove the some of the premises, we can also introduce false or negated premises, or we can perturb the conclusions so that but the final outcome is the same, that like there's no valid implication chain anymore that can derive the query. And the parameters here are basically similar, like reasoning depth and number of edges in the graph, so things like that. So this table shows like there are some logical like inference rules, and these are what we used to construct every single edge. So for example, on the previous slide, we have node B and F. So the way we connect B and F can be done through one of these following implication rules. So now we have constructed the data set, and we try to answer the first research question: how do untrained models perform on reasoning tasks of varying deductive difficulty? So here we test three models. All are Kuhn model, but one of them is Kuhn 2.5, and the other two is Kuhn 3. So to answer the first research question, we should know that if the model performs perfectly on the tasks we have, it means that the model should have the two capabilities here. The first one is that the model should be able to follow the valid reasoning path, which means the model should try to traverse through the whole graph from the given root premise to the final query node. And the second capability is recognizing unanswerability. So basically, if when the model is traversing the graph and it figures out that it is impossible to derive the final conclusion, it should be honest and brave to acknowledge that this question is unanswerable instead of trying to generate some random answer. So basically, we tested the three models on some graph LA data sets with varying parameters. So in this figure here, we show their performance according to different number of variables involved when constructing the data set and different reasoning depths involved. So basically, we observed that for answerable cases, which are the top three like subplots, the model's performance decreases as we increase the reasoning depth and as we increase the number of variables. And when the number of variables involved in the graph are 13, and when the reasoning depth is about 12, all the Kuhn models, they just achieve like almost trivial accuracy on the answerable case. And for the bottom row, we have the unanswerable case. And here we found like Kuhn 2.5 3B, the performance is slightly better, but for example, Kuhn 3 1.7B, the performance is still low. It's still like pretty low when number of variables and reasoning depth becomes larger. So some takeaways for these results on graph LA is that these models, they struggle to follow the multi-step derivation passes when we check their output trajectories. And basically none of these models can reliably demonstrate the correct behavior for multi-step reasoning. And they are not honest in answer the questions. And again, sorry, this should be RQ1 here. So for results on graph LI, we have some similar observation. So for graph LI, it is a binary classification task where the question will only ask about whether the final conclusion node is true or false. So like previously for graph LA, the question will be try to calculate the actual value of the conclusion node because it is linear algebra. But for graph LI here is logical inference. So the task is binary classification. This means that by random choice, the model should achieve 0.5 performance. But here, as you can see, as the number of irrelevant edges and the reasoning depth becomes larger, all the three models, they achieve even lower performance than 0.5. So we further checked their output trajectory, and we found that the lower performance is basically due to the fact that the model cannot generate responses that follows our format. So the performance is further below 0.5. But basically, the issue remains the same on graph LI datasets, which is that all the models like their performance decreases as reasoning depth and complexity grow. So after this RQ1, our takeaway is that all the three models through prompting, they just fail on our task. So this leads to our second research question. How can training equip those models with honest reasoning capabilities? So before answering RQ2, we explore some existing methods, including SFT and GRPO. So both these algorithms, they have some limitations that are like clear to everyone. So for SFT, as explained before, like it cannot robustly generalize beyond the demonstrations given in the training set. And for GRPO, they suffer from the zero variance issue, especially when the data set is difficulty is like this, where the model performance is just like quite close to zero, quite close to trivial performance. This will more like largely affect the collapse for GRPO. So to solve those issues, we propose the method named Anchor. It addresses those issues by injecting the ground truth reasoning trajectory into every rollout group, as if the ground truth trajectory is one of the model's rollout. So this method ensures a consistently positive optimization signal that prevents zero variance issue even at the beginning of the training if the dataset is extremely difficult. So to understand it further, this anchor method augments GRPO with an SFT-like term. So this term basically like unifies the supervised guidance with the GRPO's policy optimization. So as a result, it can enable more reliable gradient updates when traditional GRPO would fail for those cases. So for the algorithm, we have some like proposition showing that the gradient update for Anchor basically it contains some additive term where this term is basically always like positive because the trajectory we inject to the model's rollout is a ground truth, right? So there will be always positive rewards given to this trajectory. And as a result, when it comes to the gradient update, the signal here will always be positive. But as shown here, this update is still like constrained by like RL, some RL features such as clipping. So this makes sure that the gradient update will not be too much if the distribution is further beyond the base model's distribution. So to compare, or say to assess the anchor approach, we compare anchor against several baselines. So one of the most simplest baseline is COT. So COT is used in RQ1 as well. And some other training baselines, including SFT, GRPO, and a combined approach where we first train the model using the SFT loss, and then we train the checkpoint and continue train the checkpoint using GRPO. And we also explore the curriculum learning setting where we first train GRPO on some easier data sets. So the easy data set is manually constructed by us, which is easier than the final training set. So basically we measure the accuracy overall and accuracy on answerable subsets and accuracy on unanswerable subsets as the evaluation metric. So this table shows the results of anchor comparing to the existing baselines. So all the values here are accuracy, and this column named overall means the overall accuracy, and unanswerable accuracy and answerable accuracy. And we have the results all in one table for the three models. So some takeaway for these results are first, we observed that prompting just achieves quite close to the random performance. As you can see, no matter like which model is tested and which subset we try to test, the performance are quite low. So this means all the models they fail at the two tasks before any training. And for SFT, the performance is closer to the majority class prediction. So basically, it means that for GraphLA dataset, since the question will be something like try to calculate the value of the conclusion variable, right? So when we train the model on the training set, even though the training set is balanced for answerable and unanswerable set, the model's performance will like the model can still hack the balanced data set, because without any traversal, the model can just blindly answer with I don't know or unknown for all the cases. So this means that the model doesn't even need to perform the tree traversal to answer this question to get 0.5 overall performance. So we observed that SFT, as a result, they basically trained the model to always predict the I don't know or unknown all the time, regardless of the like what the actual instance is. So GRPO is quite similar because when we checked about the model's output trajectory in the middle of training, we found that because like at the beginning of training, the dataset is too difficult, the model fails to learn the correct signal. So the model will instead tries to hack the reward by always predicting unknown here. And as a result, GRPO achieves like more extreme results where like it will fully hack the the metric, and they will achieve perfect performance on answerable cases. But for answerable cases, it will still always output unknown, so that the performance here doesn't like make sense at all. So in comparison, there are two other baselines, right? So the first additional baseline is we first do SFT and then do GRPO. But unfortunately, on the two data sets, this method is still quite similar to GRPO or SFT results. The actual interesting thing is the curriculum learning setting. So we observe here that for curriculum learning, on some models and on some data sets, it can perform pretty good, achieve a pretty good performance on the two data sets. But remember, the easy dataset is manually constructed by us. So this means that we can control the difficulty of the easy dataset by varying the number of reasoning depths and the hyperparameter values. So this result shown here is already the one that we have gone through extensive like exploration of how easy the dataset should be, so that the model could like actually learn on the easy dataset as the first training stage, and also the model will like continue learning on the final target hard dataset. So the results here is you can view it as an upper bound of the curriculum learning setting. So for our method anchor, we found compared to almost all the baselines, it achieves the highest performance. So basically, like it outperforms all the baselines except for curriculum learning in some of the settings. And we also do some compilation by adding the anchor method to the curriculum learning setting, and it will further improve the performance on almost all the settings. So here are some like textual summary of the results. So on graph LA, we observed that most baselines, they just fail to learn the task, while curriculum learning works for some larger models. And in contrast, Anchor can consistently succeed across all the model sizes, and they have strong performance compared to the baselines. And same thing for graph LI. So now we have some further explorations or say analysis on why Anchor works. So we first compare Anchor with traditional GRPO approach. So as shown in the figure on the right, we have we monitor two metrics in the procedure of training. So one of them is the gradient norm, and another one is a clipping fraction. So basically, we found that Anchor, the reason that Anchor produced the stable learning dynamics is that they have a very smooth decrease of the gradient norms and clipping fractions compared to GRPO. You can see that GRPO here exhibits quite noisy and unstable updates. And another discussion is about curriculum learning. So basically, we in the paper we show two different difficulty versions of the easy dataset, and here we illustrate like how curriculum learning is not robust, like according to the difficulty of the easy dataset. So as you can see here, we use two of the three models for illustration, and on graph LA we compare the curriculum learning with traditional GRPO. So the GRPO algorithm learning trajectory is colored blue, and we have two different versions of the easy dataset. So one of the easy dataset is constructed under the hyperparameter where the number of variables equals 5, and another one is number of variables equals 8. So this means the first one gives a easier easy dataset compared to the second one. And you can see here that for like when we train on the easier easy dataset first, the model accuracy will achieve pretty high after training several steps. But this means that this difficulty version will give the model enough like signal so that like after training on the easy dataset, the model will further train on the hard target dataset, and it will still have some non-trivial performance in the end. But if we observe the performance of Coin 2.5 3B on the left figure for the harder easy dataset, we will find that after training on this dataset, the performance will still be trivial because this dataset is too hard for model to learn, even though we have GRPO. So basically, in this case, we can view this harder easy dataset as the hard dataset, and in this case, we have the same issue where we had for training GRPO on the target dataset. So the differences between these two models show that there are some like factors that can affect the curriculum learning performance. So as a result, we conclude that curriculum learning is fragile, and it is highly sensitive to the dataset model mismatch. So like anchor instead have a more robust behavior. And the last discussion is like we do some evaluations by combining anchor with the curriculum learning setting, and we found it yields the strongest performance. Yeah, so here we highlight the combined approach performance here. So beyond training for like the optimizing for the final outcome, we also explore the multiple process rewards as a beginning of this project. But the reason why we do not include process reward results is that all of the process reward fail in this setting. So basically, we experimented with a broad range of process rewards, including different ways of extracting the steps and different ways of giving to the thinking token and giving the final answer token. And we have different ways of evaluations, either through rule-based evaluation for the process reward, or through language model as a judge for the process reward. But for all those settings, none of them yield meaningful improvement signal. This means like all the approaches here that we have tried are like they all lead to trivial performance, same as GRPO or SFT. So our intuition is that process rewards is very hard to design, because in our case, especially in our data set, it is very hard to know whether a generation should be separated into how many number of steps and how we should give rewards to each step. So here, as a takeaway, we claim that like Anchor is a very simple approach where it doesn't use any process rewards. It just uses ground truth trajectory, but it provides some meaningful signals for honesty alignment in the deductive reasoning setting. And for future work, one thing, we can test larger models, but constrained by computational resources, we are unable to do that in this paper. Even though like we observe some consistent behavior across all the three models, testing larger models can be more helpful to demonstrate the robustness. And secondly, we restrict our study to controlled deductive reasoning. So after this very clean setting, we can, as a follow-up work, we can explore whether our approach can be applied to the cases where like a factual recall also is also confounding the final honesty behavior. So basically, it means that extending our current analysis to settings that mix deductive reasoning with external knowledge or other existing RL algorithms could be interesting to explore. Yeah, so that is all for the presentation for this paper.
Thank you, Jiarui, for this wonderful talk, and very solid and a lot of things basically.
Thanks.
So okay,
Thanks.
so one question from like the audience is, it's a very good introduction question. So how is honesty defined here?
Yeah, good question. So right, so we have some concrete definitions in the paper. Basically, honesty that we use this term is that we want to yeah, so basically like honesty means that the model should not fabricate information. So this is a one short sentence of honesty definition. But behind this sentence, honesty has two dimensions when a language model tries to generate an answer. So here are the two dimensions behind like not fabricating information. So the first dimension is like if the question is valid but challenging, the model should try to acknowledge its own knowledge boundaries in the valid questions. And the second, if the question is invalid, the model should point this out rather than trying to make up an answer. So in our paper, we exclusively study the second dimension rather than the first dimension.
Okay. So to me, one question I have when reading this definition is, so honesty is usually defined in the first way, like They should
Yeah.
okay, sorry.
Mhm.
Yeah, they should know their own knowledge boundary or ability boundary. So for example, like when I saw your paper first, what
Mhm.
I thought about the definition of honesty would be like, okay, if the model is uncertain about
Mhm.
their answer, then they should refrain from answering it. And we can kind of construct this data set also like easily. For example, if given a data point, you just sample say 50 times, and if like over 40 times they are
Mhm.
answering wrongly or like answering random things,
Mhm.
then we should train the model in those situations to like answer that I don't know. So I think so to me, like honesty to me usually refers to like whether I am honesty about myself or like whether the model is honest about itself.
Mhm.
And then the second definition is more like whether the model know how to do linear algebra or how to do logical reasoning in an accurate way. Um, so so I
Mhm.
feel
Yeah.
like what's kind of the difference between say the model's performance on the specific domain, say linear algebra, and the model
Mhm.
is being honest in
Right.
linear algebra.
Right. Um, yeah, so this is a good question. So we briefly explained um, the capabilities to that the model should have to perform well on the data set. Um, so basically, um, as shown in this slide, like there are two capabilities involved to perform well on the data set that we construct. So the first one is that the model should follow the valid reasoning path. I think this is what you mentioned. Uh, uh,
Mm-hmm.
yeah, and the second one is that the model should also try to recognize the unanswerability after following the reasoning path. So in reality, when we check the model outputs um, in almost half of the cases, like without any training, the model will just try to follow some part of the reasoning path, and it just do some early exit by saying that, oh, this question is not solvable. But in reality, without any actual calculation, the model uh, should know the question is answerable or not. This means that the second capability is uh, a complement to the first dimension. And here, in this paper, we when we test about the model's performance, we treat the two capabilities together as a whole, and we define honesty on deductive reasoning in this way that like it covers the both dimensions.
I see. I see. Okay,
Yeah.
I think this is very interesting.
Mm,
Uh, okay. So then I'm curious. So, in your evaluation, it seems more like outcome-based evaluation,
mm.
both in evaluation and in training time. So, I'm wondering, like, do you have an error analysis on what on like how the model fails on what percentage, etc.?
Uh, you mean for the reasoning procedure or um, the still the final answer?
Um, yeah, so I'm wondering, for example,
Mhm.
whether the model is making a wrong reasoning, in their reasoning train, or or
Mhm.
as you say, like they are kind of making the right one, but do
Mhm.
some early exit
I
or
see.
like etc.
I see. Yeah. So without any training, we observed that for Quinn models, they have some initial capabilities to follow the reasoning chains. So basically, for all the three models, we found without any training, the model will first try to solve the problem by uh, like maybe imitating some of the behavior in the training data set where the model will start with some sentences like, let's define some variables A, B, C, D, and let's try to extract the linear equation explained in the question. So basically, when checking the model output trajectories, we found those signals where the model is actually trying to engage to dive in and try to solve the problem. But the issue is that the model will not be able to fully or say correctly follow the reasoning path, so that when the dataset difficulty is higher, the model's performance will decrease exponentially. So this means that those existing models, they are probably trained on some very easy data sets like this. But when the dataset difficulty is higher, the model will be unable to fully follow the reasoning path anymore. So basically, that is also the takeaway from this figure. But after training, so after say SFT or GRPO, we surprisingly find the model just will just answer I don't know all the time without even trying to make a guess or like trying to make an attempt to solve the question. So we explained that like the failure mode for this may because of that the model doesn't need any actual graph traversal to answer unknown, so that the model will just answer unknown all the time. But after using our method anchor, we found the model will have a positive learning signal at the beginning of training. So this means that even if the model itself generates all the rollouts wrongly, we explicitly instruct the model which like where the model should try to like push itself forwards. So this means that at the beginning of training, the model will have some positive learning signal. And when we check the model outputs, we find that this actually helps the model to avoid hacking the reward directly. So the model will maintain the original behavior when we do prompting, and as the training procedure goes, like the model capability will become like better and better. So basically, when the data set the difficulty is higher, the model will try to learn to adapt to the to that difficulty version. So yeah, so I think this is how model output works in like either without training or with training.
I see. Okay. Okay.
Mm.
Thank you for this very comprehensive answer.
Sure.
Another question I'm wondering is
Mm.
that I think in the training stability time, also like the training signal time, you inject this ground truth answer into the trajectories.
Mm.
So one reason is that okay, when all trajectories are wrong, then you don't have any meaningful training signals. So
Mm.
I think there are many algorithms such as DAPO or Doctor GRPO
Mm.
that's kind of doing the same thing by removing those data points that all answer wrongly or all answer correctly.
Mm.
So I'm wondering, have you tried them? Do they have like a similar performance if you also use them in an easy to hard data curriculum?
Right, this is a good question actually. So we tried Doctor GRPO, but the performance is exactly the same as GRPO. So we don't include
I
the
see.
performance of Doctor GRPO in the paper. We didn't try other methods such as PSFT or like so there are a lot of other like RL
Mhm.
papers that like introduce some like external patching to the current GRPO algorithm by
Yeah.
either saying like we remove some data points or so things like that. But our claim here is that we think those methods are not very elegant in this case. But
Okay.
yeah, so this is why we didn't compare our method with them, because we think there's no like there's not uh, uh, like this not too too meaningful for us to compare. Uh, like even though their method, even if their method works on this setting, it doesn't mean that there is a like robust algorithm that can be applied elsewhere.
I
Um,
see.
yeah.
Okay, okay. Thank you again for this answer. I think we are running out of time. We actually go over time by 6 minutes.
Okay.
So
Sorry.
thank you very much, Jerry, today for this wonderful presentation and the interesting findings. And thank you all for questions from the audience. Um, so that'll be the talk today. Thank you, everyone.
Yeah. Thank you, everyone. Thank you, Wenyu, for hosting.
Sure, thank you.